So I don't really think we need to do anything else except welcome Guido van Rossum, ladies and gentlemen.
Hello, can you hear me?
Yes.
Wow, this is amazing. Okay, I'm going to try to be very technical. So if you're not feeling very technical this morning, still a little tired from last night's party, it's okay if you leave. So not too long ago, actually, about half a year ago on Python Ideas, someone innocently asked or started proposing making some changes to async core under the wonderful title, Async Core Included Batteries Don't Fit. I think I have the first page of the message here. This was very quickly evolved into a Senti thread. I was piqued by the topic. I knew that async stuff was sort of controversial. There were lots of ways of doing it. And I decided to dive in and sort of, what prompted me to dive in? Well, I had just done a whole bunch of asynchronous stuff, including novel async API design for Google App Engine. And so I felt that unlike previous times when asynchronous stuff came up, I actually had some understanding of why people cared about async APIs and why it was so controversial. So let's take a deep breath. What is asynchronous I/O? Well, deep down at the bottom, it's whenever you're waiting for I/O and you're also doing something else, which is as opposed to the normal sort of default operation of Python and most other programming languages where you say input, and then your program is not capable of doing anything until the user actually typed a line of text. Asynchronous I/O is actually as old as computers because back in 1945, the input devices that they had were also much slower than the central processing unit. So there are lots of approaches, interrupts, threads, callbacks, events, and I'll get back to more about what sort of different ways of dealing with this. Let's first look a little bit at why do you want asynchronous I/O? Why do people say we need asynchronous I/O in the standard library? Where does it come from? Well, as I said, I/O is slow, and since the CPU is mostly not needed for handling any of that, if you have a bunch of different things that you all need to be done, it would be great if you could keep doing some of the things that do use the CPU while you're also waiting for your I/O. And then at some point when the I/O is actually done, you can start doing more I/O or get the results out of that. One example that's a kind of a different approach. It doesn't have to do so much with doing multiple things at once, but keeping user interface responsive. If you click on a button, and one of the effects of that button is that it goes up to the net and fetches the URL. It's very annoying if now you get a default until the remote server finally hooks up. Burps up last night. Guido actually gave a really good talk about this 2 days ago, which unfortunately I missed, but I heard it was very good. So there are other reasons also. One important reason is actually that you have multiple things of I/O that you all need to do, and they're independent, like fetching 10 things from the web or handling 1,000 incoming connections. So there are lots of reasons why people want to use asynchronous I/O. And what is this sort of the most common tool that people go for is threads. So why not just sort of say, well, let's use threads, because threads are actually a pretty common paradigm. They're well understood. They're supported by all operating systems. And the nice thing of threads is that you can still write this simple synchronous code where you say input, and your thread is just blocking for some input to happen, for the user to enter a line or for a server to give you a packet or something. But your other threads will still run. My voice is doing funny things. I'm going to lubricate a little bit. Maybe that helps. So Unfortunately, threads have their limits. Operating system threads, as they currently exist in modern operating systems, are wonderful things, but they are kind of costly. If you have 10 threads, great. If you have 100 threads, well, depending on how powerful your machine is, you might get a little worried. If you have 1,000 threads, you're probably already using your asynchronous I/O system for handling lots of socket connections. For example, when you're in a server that just deals with lots of clients, and maybe the clients are very slow, or maybe you're intentionally HTTP long polling them. The number of sockets, operating system kernels impose limits on how much of everything you can have. You can only have so many file descriptors, there are only so many bytes of memory available, you can only have so many processors. So you can also have only a certain number of sockets open at the time. The kernel will just run out of space for them, and the maximum number of threads, like 1 or 2 orders of magnitude. So if you want to get the most out of your server machine and be able to handle as many connections as you can't have a thread per connection, because you'll run out of threads way before you run out of sockets. Finally, of course, a big problem with operating system threads, the way they work, is that they have preemptive thread scheduling, which means that at any time when your thread is running, even if it's not blocking for I/O, the scheduler can decide that you've run long enough and some other thread will run. And so now this means that if you have 2 statements running in one thread and 2 statements running in another thread, and they're somehow reading or writing the same global variable or shared variable in general, there are, 4 or 6 different ways that those statements can be interleaved. And you probably don't hit every single combination when you're writing your tests. So you end up with race conditions where the scheduler hits you at just the wrong moment when you have 2 global variables that need to be in lockstep, and one of them has been updated, the other one hasn't yet. Something like that. Of course, now we add locks to our program, and if we're really good at using locks, wow, now suddenly the program doesn't run very fast because everything's constantly waiting for that lock. So there are other ways, even though there are also, some people have proven that you can actually get quite far with threads in the most modern operating systems. It's not a completely decided answer that threads are always worse than asynchronous I/O, but they each have their their pluses and minuses. So how do you do asynchronous I/O with threads? Without threads. There are system calls like select and poll and a few others that only exist on certain platforms like epoll and KQ. There are higher level APIs on top of that in Python, like async core, which unfortunately was invented over 15 years ago and is really showing its age. It's using subclassing as an API style, and it's not very extensible in the right direction, and so on and so forth. So most people ignore that and write their own thing straight on top of select and poll. There are a bunch of things that you can get wrong, but it's also not rocket science. Bram Cohen, who is a master of internet protocols, always writes his own because he always gets better results that he claims. Or you can use an asynchronous framework. There are plenty of frameworks to choose from that support asynchronous I/O, like Twisted, Tornado, something called ZeroMQ. Or you can wrap existing C libraries. There are a number of competing C libraries that solve this problem for C programmers, and they've all gotten at least one Python wrapper as well. So there's libevent, which I think is the original, and has since evolved into libevent 2. But there's also libev, which was a better libevent. And then there was libuv, which is an even better libev, and I think libuv is popular and powerful because it's used by Node.js. But when you wrap those, you end up with a rather C-like API style. There are also completely different approaches. I think Christian Tismer started this with stackless, and then gvent built that out in a slightly different direction based on, I think, greenlets, Armin Rigo's magical tricks, and there's also something called eventlets, and there's probably a couple of more, and almost all of them have the have the greenlets at the bottom of them. There's also some overlap here. So none of these alternative approaches, even though they all solve the problem of race conditions and you want more sockets, then you can have threads and stuff like that, they all have their downsides. One of the downsides is actually that there are too many different ones. Most of them are in some way based on callbacks, the stackless G event family excluded, and nobody likes callbacks. Well, at least when I say I don't like callbacks, everybody always goes here. Because you can't really get around some level of callbacks, the APIs are usually pretty complicated. And the standard library is of very little use once you're using an asynchronous framework. And now, of course, everybody who knows anything about G-Event is saying, yes, but G-Event solves all that. And yet G-Event is somehow, to me, it doesn't do it. It has really scary implementation details in the greenlets level. It's pretty much CPython specific. It's Intel x86 specific. It's actually really hacky C code that copies the C stack in certain situations. There's also a monkey patching approach to make the standard library sort of work. So you monkey patch the standard library and then you start using existing standard library operations like URLlib or HTTPlib, and you hope that it actually works, because you never know with this monkey patching stuff. And unfortunately, you're still not completely clear of the problem that the scheduler could, at a random moment, interrupt your task and switch to a different one. Now, if you talk to G-Event and Greenlet people, they always say, oh, you know exactly when it switches because there's a very specific call into the Greenlet API you have to make that switches. Unfortunately, any function you call can also make that call. And any function that you call today, that somehow today you happen to know that it never switches, tomorrow, someone could add a logging statement or a lazy caching or a consulting of a settings file or who knows what kind of extra optional feature, and every once in a while that function does block. And suddenly, so you're basically in the same situation as with classic OS threads, that you cannot really trust when you will be switched and when you won't be switched. And the worst part is that if you're not careful, you can still run into the situation where you don't switch enough, and one stupid thread that's somehow sitting in a tight loop can completely use up all the CPU, and all the other tasks waiting for I/O won't do it. So I can't help it, but I would like a system where I can actually tell whether a particular line of code is possibly suspending the current task or thread or not. So what are we going to do? Courtesy Randall. Of course, we're going to introduce yet another standard framework that's going to replace all the other standard frameworks. Seriously. Let's finally standardize that event loop. Because at the bottom of all of these, including G-Event, there is an event loop. And sort of there aren't too many choices in how you implement an event loop. And event loops, sort of, there's a certain amount of functionality that they have to have. They have to manage your callbacks. They have to manage your file descriptors. You have to tell it which file descriptors you care about. And one way or another, they're all sort of doing more or less the same things, but sort of how you write what you want the event loop to do is vastly different for each So So why is the event loop so special? Because on the one hand, the event loop is the thing that serializes things. The event loop is the thing that guarantees that while your code is running, no other code will also be running. And given that Python has a global interpreter lock, there's not actually all that much advantage in having other code running while your code is running, because you're not making more progress together. So this serializing of events is a very powerful mechanism if it's done right, because it gives you the knowledge that no one else is going to mess with the global state or the shared state until you say that you're done with it. So you have sort of implicit locking. Of course, in order for this to work, you can only have one event loop. And this is why the event loop is so special and why it's important to sort of move the standard event, the event loop into the standard library and sort of take ownership of that thing. Because there should really be only one event loop. You can't have the twisted event loop and the G event loop in a single process. Because they would just be sort of competing for who is the only one that's currently running, and sort of switching between them carefully is not very effective. So because each framework has its own event loop, they don't really interoperate very well. So I went back and I looked at a whole bunch of different frameworks and specifically at their event loops, and I also talked to a bunch of people. Thank you, Gliv. Thank you, Ben Darnell. Thank you, various other people. What you have is there's an event loop. It runs or it doesn't run. Usually there are ways to start it and to stop it. Occasionally the event loop is just always running. But usually you have to somehow manage it. You also have to access it. Then a very fundamental thing is, here's a function. I want this function called at some point in the future. That point in the future may be like right now, like right after the current event handler is finished, or it might be at a specific number of seconds or milliseconds in the future. There's a variant there where you say, well, here's a function that I would like to call every 2 seconds or so. And the final piece of functionality is, I have a file descriptor, or maybe some other object that represents I/O activity to the operating system. And there's some asynchronous I/O going on that file descriptor or that I/O object. And I want to know when that is ready. And depending on which paradigm you're using, on Unix it's usually sort of, when is the thing ready so I can start reading, at least start attempting to read or write. Windows IOCP has a different model where you say, I want to do this type of I/O, and then you want to know when is the I/O done. So ready and done are two different paradigms, and we'll get back to that. But that's about all you need in an event loop. And you need it to sort of abstract over the different possibilities for actually asking the operating system to multiplex the I/O. So you want to have an intelligent switch between select and poll and epoll and everything else. So hopefully, with some luck, a unified event loop could actually solve the problem that the frameworks that currently exist don't interoperate very well. Now, actually, why is it so important that the frameworks can interoperate? Well, the reason is that every framework has its strengths and its weaknesses. If you want to have good implementations of esoteric internet protocols that have been debugged for a long time, Twisted is your friend. If you want to do web server stuff, maybe Tornado is what you want. Having Tornado and Twisted work together, at least when Tornado originally came out, was impossible. I've heard, I have not verified, that Tornado now has a separate adapter that says you can actually use Tornado in combination with Twisted. So for that particular pairwise combination, interop has been solved. On the other hand, there's no way that you could run Twisted with the Tornado main loop. So the Tornado people just sort of give up and say, use this other main event loop and adapt it. There are a few others of those, but it's easy to find sort of pairs of frameworks that have no way to interoperate, or you'd have to run one in one thread and another in another thread, and then you lose a lot of the advantages. So this is where PEP 3156 came in, and a reminder, unfortunately, we're violating this wonderful directive of not trying to solve the problem of too many standards by adding one. We're still adding one. But this one can actually be called standard because it will be in the standard library. Yes, I really know this is madness. Everyone has their favorite framework. Let's just move twisted. The first response, actually, to that long and well thought out message about fixing async core, the first response was a one-liner that said, why don't we, I think it said, so you just want twisted in the standard library. And there was a lot of disagreement after that. Yeah, if I personally believed in G-events, we could put that in the standard library and say everything in the standard library is always using G-events. That probably would leave a large number of people unhappy nevertheless. Also, I mean, the right way to do that would probably to go back even further in history and sort of adopt stackless Python, which was always intended to be eventually become a part of standard Python. And I've always held off on that for reasons similar to what I mentioned about G-event. So I'm still not doing that. Yeah, why not rep one of the industry standards that exist at the C level? Well, okay, there are still too many to choose. So I just made up my own. I did, but I didn't completely make it up. I actually looked around and sort of, I felt what are the problems that everyone needs to solve. Like there's this thing with, you need to be able to, everything needs to work regardless of whether underneath you're using select or poll or epoll or KQ. Those things need to be completely abstracted away, because they're just all different ways of doing exactly the same thing, which is asking a Unix kernel or some flavor of Unix, giving it a bunch of file descriptors and ask when some of them are ready for I/O again. Other things that sort of are obvious is the callbacks I mentioned, timed callbacks, all those things. So I looked around, I came up with my own minimal version. Originally my minimal version was truly minimal. Everything was in one file. It only worked on Unix. Then I started comparing nodes with other frameworks. I looked at the Tornado event loop, and it looked pretty similar. So I thought, okay, well, I guess even if I start in a vacuum, I can come up with something that's pretty close to what other people have come up with too. But there were some differences, and there were some tricks that I had missed, and there were also some dubious design choices that I decided not to copy. And then I looked to Twisted, and I couldn't actually find where the code was, so I called Glyph, and we had a bunch of very productive meetings where he completely brainwashed me, and now I'm a Twisted fan, but not really. But there's something inside Twisted that I really like, and that's abstractions that are slightly higher level than select-based. Because on Windows there's this thing called IOCP that works very differently. I've been mentioning that a few times. And so the importance of that was really rubbed in by the meetings with Glyph. And also the importance of having abstractions corresponding roughly to what Twisted calls transports and protocols. And I figured those were great names, so why not call them transports and protocols, although they don't have exactly the same API as Twisted. Lawrence van Houtven had also, a few years ago, written something called the async PEP. It's PEP 3153. Actually, this PEP is 3156 because I wanted to sort of honor Lawrence's PEP by having a nearby number. Otherwise, it could have been PEP 400 or so. So I started iterating, and then people started contributing and reviewing, and I wrote a PEP. And now it's perhaps a little confusing. What is PEP? What is PEP 3156 and what is Tulip? Because I use the code name Tulip for the code that I'm writing, but I'm using PEP 3156 for the interface. So the PEP is a proposal to adopt a certain standard interface for event loops, and to also have a default implementation of that interface in the standard library in Python 3.4. Tulip is my implementation of that standard event loop interface. It's also the prototype where I sort of experiment if I think, oh, maybe I should change the names of all these methods to be a little different, or maybe the signature of this group of methods needs to be changed. I code it up in Tulip first, and then if it works, I update the PEP to match what I wrote. There's also stuff in Tulip that's not meant to be part of the PEP, not meant to be part of the standard library, but which is application code where I try to sort of use all this stuff from the perspective of an application developer. And so I go in sort of application user mode, using Tulip without writing Tulip. And I try to write, I wrote a little web crawler, I wrote a little web server, and I sort of try to feel, is this actually a nice way of writing an application? And usually I come back with, oh yeah, there's a bunch of missing stuff in Tulip and in the PEP that I need to add. So eventually I hope that Tulip will be the reference implementation and incorporated under a better name into the standard library. It may also forever after become a repository for additional functionality that doesn't belong in the standard library, or is sort of where there are too many different choices, where Tulip's choice is just one of the possible choices. And in addition, Tulip will be what you can use all this new asynchronous I/O stuff with Python 3.3, where it's not yet in the standard library. And of course, I'm running out of time much sooner than anticipated. It is my want, so I'll try to speed up. So the PEP does not just propose an event loop, even though the event loop is the sort of the building block for interoperability. In order to sort of encourage interoperability, the PEP also has a small API to change the event loop. There's a way where you can say, set the event loop to this particular object that implements the standard API. There are a few quirks there. So that is sort of another framework can plug in their event loop through an adapter. And all the Tulip application level code that just uses the standard API will still work. So now you can have Tulip code or random user code written against the new standard, and G-event code that uses the G-event paradigm in the same application. And you could do the same thing with Tulip and Twisted or Tulip and Tornado. And hopefully even with multiple of these, because eventually I hope that the various frameworks will also make an effort to adapt the standard event loop API to their paradigm, so that it would be great if even 80% of the Twisted protocol implementations actually worked with the standard Tulip event loop rather than with the Twisted event loop adapted to the standard protocol. But there's more to the PEP, and people have suggested that I should split it in two PEPs, which is still an option. On the other hand, the two things are quite related. So let's get back. No, let's not get back yet to the new paradigm for writing asynchronous code. Let's first say a bit more about the event loop. I think I already mentioned a bunch of this. So I have had some of the people who are stakeholders in this world review it. I'm going to sprint on it Monday and Tuesday. And that could include ripping out parts of the PEP and rewriting them and all that nice stuff. The event loop has sort of a bunch of different groups of methods, and maybe I'll just race through this because this is getting pretty detailed. So there's ways to manage the loop, basic callbacks, callbacks related to I/O. There's some stuff necessary to interact with threads. There's even stuff necessary to interact with Unix signals, although clearly when signals don't work on your OS, then they don't work. Then there are some sockets. There's some socket stuff that's mostly used for transports, and a bunch of higher level socket operations that I hope will be popular among application programmers. So to start the loop, there are way too many run functions, and to stop it, there's a stop function. We'll probably refactor this API. Basic callbacks, call soon, call later, which is takes a delay, call repeatedly, which sets up a timer. Call soon thread save is when you're in a different thread and you want to add a callback to an event loop running in another thread. That's kind of esoteric. All these return an object which I call a handler, which may not be the best name, but it's also not the worst name. For a while it was called callback, but that was too confusing. There were too many things named callback already. That handler, the main purpose of returning a handler is so that we don't have to have explicit methods that revoke all these callbacks. You just say cancel, call cancel on the handler, and then your callback is no longer going to run. And so if you call cancel after it already ran, well, that's too late, unless it was a timer. On the other hand, if you call cancel before it actually has gotten a chance to run, then it will never run. So there's callbacks for I/O, and these wrap the abstractions that take care of using select or poll and so on, add a reader callback, add a writer callback, or remove them. Exactly what is a file descriptor here? There's some fuzziness that's intentional. For example, on Windows, if you're using select, it can only be a socket, because even though both sockets and disk files have things called file descriptors in the sort of the simulated Unix environment that we use on Windows, they're actually completely incompatible objects, and the select call only works with sockets, so that's a Windows restriction. On the other hand, on Unix, you could use a pipe or a sudo TTY or a few other things. I wouldn't recommend using a disk file because the typical Unix kernel says that a disk file is always ready. But sort of that's more about the semantics of select than anything else. It could also be an object that has a file no method because all the poll and select functions support that. So there's a way to deal with signals, not recommended. There's a way to say, well, I have a function that unfortunately is going to make blocking I/O calls, and I have no way to re-implement that. A good example is getAtterInfo in the socket module, which is the fundamental way of making doing a DNS lookup. That's called synchronous. That function is synchronous, and it can certainly block for I/O because it itself wraps other abstractions in the C library that might do I/O. So there's no way to avoid that. So you basically, either you can't use it or you have to run it in a different thread. So we chose to actually accept that this is a useful function that cannot live completely in the nice asynchronous I/O paradigm. And so we run it in something called an executor, which is essentially a thread pool. And it returns a future that you can wait for the result. Then there's a bunch of low-level socket I/O operations that only transport should use. Then there are high-level network operations, like calling getAtterInfo is actually a method on the event loop, because the event loop sort of acknowledges that most likely you're going to do lots of socket I/O with it. So looking up hosts and ports without actually attempting to connect is sometimes a useful thing. You could also do the reverse lookup. And so then there's create connection, which sets up a TCP connection to a remote server. And there is start serving, which does the opposite. It sets you up as a server accepting incoming connections. I'll get back to that a little later. So these are the things that you would use in sort of application code or in code that is implementing new internet protocols like HTTP or SMTP. So you notice that I mentioned futures a few times. A future is that actually it's a pretty generic concept. It represents a value that hasn't been computed yet, but if you wait for it, you will get the value. In Python 3.2, we introduced a standard future class and a standard API for futures in the standard library, PEP 3148. This is a summary of the API. I'm not going to read it. But we can't really use exactly that future class, because that future class is designed to work with threads. So when you call result, it just suspends the current thread until the value is ready, and that's exactly the opposite of what you want. And wait a second. Yeah, so I adapted futures to work with something called coroutines. And I'll get back to coroutines in a minute. But first, okay, what is a future? Okay, I'm sorry, this looks like a duplicate slide. I'm not going to say again what a future is. Basically, it has a result which blocks and then gives you the result, or it raises an exception. So an exception is also considered a result. So it's not the same class, but it doesn't even have exactly the same API, but it's clear that they sort of are close cousins. But when PEP 3148 blocks and sort of suspends the current OS thread, we must use, drum roll please, yield from. Thanks to Greg Ewing, who proposed this first when it was on time to incorporate it in Python 2.7. Unfortunately, we got distracted by an extended bike shed. And then we got stuck in the Python 3.2 feature free. So in Python 3.3, finally, yield from is part of the language. This is an incredibly cool, but also brain-exploding thing. So unfortunately, I mean, I want to emphasize the importance of it, but I'm not going to try and teach you how it works or what you can do with it exactly. But you could write code like this, where you say, sort of create a socket, and then yield from, this actually uses all those low-level APIs that I said not to use, except when you're implementing a transport. Basically, the way to think about this is yield from is sort of this magic thing that you put in a coroutine to block without blocking, because your coroutine blocks, your coroutine is suspended, but your thread, your event loop is not blocked. Other tasks that are managed by the same event loop will now run. And your suspended coroutine gets resumed as soon as whatever thing you were waiting for, which is usually either another future or, sorry, either another coroutine or a future gets, is ready. And most of the time, the best way to think about this is actually squinting and pretending that it's not even there. If you're familiar with C#, there's something called async and await in C# 5.0. And as far as I can tell, except that they sort of have the compiler type check it, it is exactly the same concept. So their async is our coroutine, and their await is our yield from. And it would have added an await keyword to the language, except that adding new keywords is such an incredible pain. So, futures. What's the way to think about futures? Try to forget that they're there is usually the best approach. If you see code that says yield from some function and that function returns a future, then sort of the yield from and the fact that it's a future cancel each other out. And the result value that ends up in your assignment on the left is just what you'd expect from just calling the equivalent blocking function, which just gave you the data. So if you start with a function, say a read function, read takes an integer count and it returns a byte string of up to that many bytes, and it may block your current thread. So there's an asynchronous read somewhere, and it returns a future. And when you yield from that read call, what comes out of the yield from is exactly the byte string that you would expect if it was a synchronous call. That's the best I can sort of say it without bursting out in tears. The nice thing is that in all the cases where the synchronous function would raise an exception, the yield from will also raise the exact same exception. And the even cooler part, and why I'm so pushing for using yield from rather than yield, which if you write a different scheduler, you could just use yield instead of yield from. But the reason I'm pushing yield from is that with yield from, you chain your coroutines in such a way that when an exception bubbles up through a bunch of coroutine calls, all linked with yield from, you get a completely natural traceback when that exception finally hits the top level. Well, with the yield approach, the stack of calls that sort of defer to each other is all maintained by the scheduler, and it's a major pain for the scheduler to get the tracebacks right. And usually you see sort of spurious frames where you get the traceback appears to come from a completely unexpected place. And so the other thing is that the whole API of a future, the fact that it has a result method and an exception method, and it even has callbacks, you can completely forget that. Because in practice, you just call existing functions that return futures, and you use yield from to wait for the result, and that sort of replaces using result or exception. So as I mentioned, futures can also raise exceptions. And so you can catch that exception with a standard try except. So in the callback world, you sometimes have systems that design APIs where there's a callback when things go well, and an back when things don't go well, and various ways to sort of channel those callbacks and backs together and splice them apart. You can write wonderful convoluted logic with that, and you can solve all the use cases that you run into. But with try except, you can use the existing system, the existing syntax and mechanisms built into the language for sort of controlling which exceptions you handle. And it sort of all uses stuff that you already know, because you already know try except OS error. So coroutines. A coroutine really is just a generator. Yield from translates to a complicated piece of code that involves a yield. So it must be inside a generator. We have this @coroutine decorator. But actually in Tulip currently, @coroutine is an empty decorator. It doesn't do anything to the decorated function at all. We're probably going to introduce a debug coroutine decorator that checks that you're actually using the futures correctly and that you're not accidentally using yield where you should be using yield from. But sort of in normal operation, there's actually, the coroutine decorator is purely there so that the human reader of the code gets warned this code is going to use the asynchronous paradigm, and when you see yield from, it means blocking for something else that returns a future or a coroutine. Now a coroutine is not really asynchronous code by itself. A coroutine is just some code that only runs when you apply yield from to it. So coroutines by themselves don't give you concurrency or parallelism. And in fact, a coroutine that you start, but then you don't use yield from on it, it just sits there. It doesn't make any progress. It's not even going to initiate the I/O that it might be waiting for. So you really have to you can use these coroutines to break up your program into various abstract components. It's a very nice way of refactoring a large, hairy piece of logic into various subroutines, because you just link them all together with yield from and coroutines. But if you want autonomous tasks, if you actually want things to happen in parallel, you use a task. A task is actually a coroutine wrapped inside a future. The task, as soon as you start the task, the coroutine actually starts running, and it keeps running until it hits a point where it actually needs to block for I/O. There are actually two ways to create tasks. You can just use a task decorator instead of the coroutine decorator. Then whenever you call that function, it automatically creates a task. The nice thing is that that task, you can still use yield from to wait for it immediately, because it's also a future. You can also take an existing coroutine that wasn't itself meant to be parallel and say, I want this particular operation to run as a separate task. You can still, of course, later come back and ask for its result. But one thing you do, suppose you have 10 URLs that you need to fetch. You create 10 tasks for them, each fetching one of them, and then at the end you just use yield from to wait for all of them until you have all the data. Now the nice thing is that the function that actually fetches one URL doesn't have to be a task itself. It can just be a coroutine, because you can use the explicit wrapping of a coroutine inside a task. So this all works because a task is a subclass of a future, but it knows about keeping the coroutine alive and talking to the event loop. So while I'm in overtime, I have a little bit to say about those higher level network operations. You can use this to create a TCP connection, and it returns a future that only returns when the connection is actually succeeded. And what you get at that point is a transport and a protocol. And the protocol is whatever this factory function returns, because it's really a protocol factory. And so this is where this is the last point in the talk where I really have to admit, yes, I have been brainwashed by Glyph. And bless his soul. There was this async PEP that also explained why that was, but I had never really gotten it until I got Glyph to explain it to me personally. So this might explain why not everybody likes Twisted, because you have to have it explained to you by the master before you really get it. I'm going to skip all this. You can read up on transports and protocols in the PEPs. Now, there's one more thing. Below the event loop, there is this thing that interfaces with select and poll and sort of abstracts away the differences between poll and ePoll and KQ. There's a very sad story where select and ePoll take a timeout in seconds, and poll takes a timeout in milliseconds. Endless number of program bugs have been caused by that. Someone actually contributed a bunch of nice classes that abstract all that away for inclusion in the standard library. And in order to test whether they were any good, I copied his code into Tulip and started using that instead of my own feeble attempt at the same abstractions. And so far they work very well. But this will be pushed back into the standard library without being part of the PEP. There's also something called a Pro actor, which works with IOCP, which does not implement the same interface, because IOCP fundamentally has done callback semantics instead of ready callback semantics. So there's a lot more, but as I said, I'm out of time. So about that miracle. Okay, well, there's more stuff. There is a file object or a stream object that has methods like readline that return futures. There's work on a datagram protocol. There are actually some locks, although they probably won't be used much. There's a guy in Russia who's writing HTTP client and server implementation and has been contributing a lot to Tulip, actually. There's also thought of maybe modeling the whole API after requests, HTTP for humans, I think, as it's called. Oh, man, I'm glad I wedged that into the slide. And we're also working on handling subprocesses. So the interop, because the interop story is really the most important part. I mean, there are lots of cool features that Tulip will have and that PIP 3156 will push into the standard library. But if the interop story fails, I still consider it a failure, because then really it is just an example of that XKCD cartoon. So what I'm hoping is that over time, and this may take a few Python 3 releases, various frameworks will throw away their own event loop and start using the default standard event loop API. And they can do that in stages. They can sort of start by writing an adapter for their own existing event loop and use that inside their own code, but sort of use it to be able to cooperate with Tulip standard code. But eventually, if the standard event loop is similar enough to their own event loop, there's no reason for them to keep maintaining their own event loop. So I expect that only Twisted will end up still having its own reactors, because their reactors are sort of special. They do other stuff sometimes. But most of Twisted, I hope, will actually also work with the standard event loop. So this sort of, I really hope that this will help us move to a world where we can actually all get along, and you can have interoperability between G-Event and Twisted, and sort of, if as an application developer, you find a really cool piece of code that uses Twisted and you want to import that, and you have a really cool piece of G-Event code that you want to import as well, and they solve different problems in your large application, that you can actually do that without having to mess with multiple processes or rewrite it all or just forget it. If you are writing an event loop and you don't like the yield from paradigm, you can use these features completely without ever creating a coroutine or using yield from. You can just use add done callback and set result, and you will be your callback will be called when the future is ready. And you can use result and exception to find out what the result was. And so this is how I expect that at least Twisted will adapt the event loop. So when can you have it? Well, you could check out the code repo today, but I don't really recommend that, except if you want to help contribute or test it. It's very much in flux. It's very much undocumented. There are some doc strings. Obviously, there's the PEP. The PEP doesn't always match the code. The PEP has not been sufficiently reviewed. That will take some time. I hope to get several more rounds of feedback from various stakeholders and potential users. I've given myself time until November 23rd, which according to the Python 3.4 release schedule is the cutoff date for beta 1. By that time, you should also be able to download Tulip from PyPI as a third-party package that works with vanilla Python 3. And we'll keep that around for a couple releases so that if you just like Tulip and you don't care about the version in the standard library, you can use that. And we don't have a name for it yet, so suggestions. So what to do about the rest of the standard library? There's all these old interfaces, URLlib, HTTPlib, socket server. I don't know what to do about those yet, and I don't want to sort of make that fixing that a prerequisite. So we're going to think about that after all this stuff is in the standard library. So for a while there will be the classic legacy synchronous APIs and the new asynchronous APIs, and we'll have some way of merging them together eventually. And that will take years. Embarrassing alarm. So if you want to use an older version, you're pretty much out of luck. You could think about implementing the standard API again and making it available as a third-party module, but I'm not going to sort of dumb down the Tulip implementation to also support older versions of Python, because I really want to write Python 3.3 code, which is so incredibly crisp and clean, and there are so many silly things in older versions of the language that I'm so glad to be rid of. So consider this a carrot to start transitioning to Python 3.3. And lots of acknowledgements. Greg Ewing, of course, but I'll just let you read this. And so I'm sprinting tomorrow and Tuesday. So if anyone wants help, just drop me an email, guido@python.org.
Thank you very much, Guido. Always illuminating to hear what you have to say.